Hello, Gamble Montessori. This is Chad Mayhew trying to get there. I am. My face in the corner, so you're not just staring at a boring screen the whole time. Um, I'm not very good at this, but I'm going to keep trying. Okay, this is our week 2 answer key. Hopefully, you have given this a shot and now you're ready to see what the answers look like. So you'll remember there was that Thursday of spring intersession when we learned there was going to be 3 weeks off and we were all pretty excited. Um, and then that Friday we came back and the teachers on the 910A team tried to get you a packet, and that packet was specific for the 910A team, Miss Chow's team, and so what I decided to do was use, if you can look down here, right there, the week 1 of the district packet, and then jump to week 7. So the first week, which should have been spring intersession, was our week 1 work. I know some teachers assign spring intersession work, but I just thought, let's just get into it and let's start reviewing. And then week 7 was for this week, the week after spring break. Okay, so that's where we're at. And I'm going to jump into this. This is called the Freyer model, and we've never used it in class before, but Cincinnati Public Schools wanted us to use this. So it says complete separate Freyer models for the words linear function, quadratic function, and exponential function. Well, you can see that I wrote those words all here, and that you're supposed to give me some facts or characteristics. Well, on the first video, I didn't give you any, but on this video, I'm just going to do some characteristics. The linear function is our y equals mx plus b. We've seen that formula many times. Our quadratic function, we worked on that right before spring intersession. This is our y equals ax squared plus bx plus c. And now our exponential functions, which we actually did before the red ones. This is y equals a times b to the x power. We're going to be using this one today, and it may be something that you remember. I hope you do. Otherwise, this will be a good review for you. Okay, so for some examples, I'm sure you could take these general ideas and give me some examples. You could also give me some non-examples and the basic concepts. The basic concepts, you could write in something of this. A linear function makes a straight line. A quadratic function creates a parabola. And an exponential function gives us this exponential growth, which unfortunately has been talked about a lot on the news with COVID-19. And it also has this asymptotic relationship here at the bottom. So those are some basic concepts. We could also talk about this constant rate of change, this constant multiplier, and this quadratic growth, this squaring growth as well. But again, I'll leave that a little bit to you to just jot down some notes of what you understand and remember. The Freyer model is really for you just to have a pictograph. Is that a word? I think it's a word. To talk about these. All right, moving on. And my head's too big. I gotta shrink my head a little bit. I'm gonna. Ooh, I did it. Okay, so this was the first question, and the first question says a bond is initially bought for $250. So here it says decades since the bond was bought. 0 decades since the bond was bought, meaning the moment it was bought is the 0. I'm going to write 250 right here. It has been 0 decades since it was bought. It was just bought. It doubles in value every decade. Okay, part A, complete the table. It's doubling in value. So what I'm just going to be doing right here is taking the previous number and doing a times 2 over and over. It is doubling. So that's what it looks like. And I double 250, I get 500. I double 500, I get 1,000. I double 1,000. I double 1,000, I get 2,000. Here is now where we get into that variable thought. What happens if I double it d times? Well, we'll get into that in just a minute. How many decades does it take before the bond is worth more than $10,000? Well, in order to figure that out, I think I would need to keep this table going. So I'm going to skip that D value for a minute and then keep going, keep going, keep going with my doubling. So I'm looking at 3 decades was 2,000, so 4 decades should be double 2,000. 5 decades, double 4,000. 6 decades, double 8,000. And the question, how many decades does it take before the bond is worth more than 10,000? So it jumped from 8 to 16 here, and it's going to be 6 decades was the number of decades before it was worth more. Okay, now we're going to write an equation. Well, just a minute ago on the previous slide, I was talking about this y equals a times b to the x power as our exponential function, which is that repeating multiplication. So I'm going to use this y equals a times b to the x power as the standard form of my exponential function. You may remember from class that a is the starting amount and b is the constant multiplier. Oops, that's not an n. I'm still learning how to write on this. Ooh, fancy, fancy schmoo. Okay, so if I were to do this with y's and x's, I would say that my starting amount was this and my constant multiplier was this. So I'm going to start with y's and x's. Y equals my starting amount times my constant multiplier to the x power. I like to think in terms of y and x. I'm just comfortable with it. And now it says, write an equation relating V, the value of the bond. Well, this is the value of the bond. So my value of my bond is my output. That's going to be my V term. The number of decades since it was bought is my X value. So I'm going to change this to the variable D. And a lot of times on these word problems, they want you to use the letters that they want you to use. So we have to get comfortable with that. I'm going to rewrite this simply with V. The value of the bond is the $250 times the number of doublings it takes depending on which decade you want. Okay, so what does this D mean? This D simply means that. It means it wants me to write this expression over here. It's 250 times 2 to the D power. Why are they asking this 2 different times? I don't know. I don't know. Because they are. They asked it 2 different ways. I did not make this handout, so you can't blame me. I'm just trying to help you with it. There you go. Okay, anything else on this? Nope, that was all of that. Okay, so hopefully that helped you a little bit, and we're going to move on to the very last problem. This was kind of a short set. It's not the very last problem. We got some more to do. And my head's too big again. I got to shrink my head down and move my head. Okay, here are some equations. Find the solution to each using what you know about exponent rules. Okay, be prepared to explain your reasoning. Well, here's what I want you to remember from this whole exponent rule thought. We talked about x squared times x to the 5th power equals something. And you may remember this, you may not. X squared, though, literally meant x times x. X to the 5th literally meant x times x times x times x times x, 5 x's in a row. This red dot here is just this red dot. So in order to remember what x squared times x to the 5th was, we expanded that notation. X squared times x to the 5th really just looks like 1, 2, 3, 4, 5, 6, 7. 7 x's in a row. And multiplying 7 x's in a row can be written as x to the 7th power. Okay, take that thought and bring it back over here. 9 to the something times 9 to the 7th equals 9 to the 7th. Well, 2 plus 5 is 7. So something plus 7 equals 7. What I'm looking for is that number, and I think that number is going to be 9 to the 0 power times 9 to the 7th power equals 9 to the 7th power. So how do we explain the reasoning? We can explain the reasoning through the general rule of multiplying exponents with the same bases is a to the mth times a to the nth equals a to the m plus n. That's what you'd see in any textbook or on any website that refers to algebra. So we could say that 0 plus 7 equals 7, and that's how we obtained the 0 right there. That would be one way to explain it. We might also be able to talk about 5 to the 0 power, and you may remember this from our class, but 5 to the 0 power, 2 to the 0 power, or anything raised to the 0 power is always the exact same number. 5 to the 0 is 1, 2 to the 0 is 1, x to the 0 is 1. So if we explained it this way, 1 times 9 to the 7th equals 9 to the 7th. It would be an alternate way to explain the answer. Hope that helps. Okay, down here, 9 to the 12th divided by something equals 9 to the 12th. Well, any number divided by 1 equals that same number, so I would want this to be a 1 again. What could I put in the exponent where the question mark is to create 1? Thoughts? You guessed it, I'm going to put a 0 there. 9 to the 12th? Uh-oh, where'd my colors go? 9 to the 12th divided by 9 to the 0 equals 9 to the 12th. And there we have it. Now, there is an alternate explanation. You may remember that we did things of this nature in class as well. X to the 5th over x squared literally means 5 x's in a row being multiplied over 2 x's in a row being multiplied. You may remember that any number divided by itself is 1, so this would give us a final answer of x to the 3rd. That in fact, a to the m over a to the n is equal to a to the m minus n. That when the like bases with exponents are in a division problem, we subtract. When the like bases with exponents are in a multiplication, we add those exponents. So we could also talk about 12 minus 0 is 12, an alternate explanation. Whew, that's a lot of math. Okay, so we went through that, and let's go through the very last set. In a biology lab, 500 bacteria reproduce by splitting every hour on the hour. Each bacterium splits into 2 bacteria. So this is another times 2 problem. I don't know why the district wanted us to do 2 of these problems that acted almost identical, but they do, so we'll do them. What I'm doing right now is I'm writing in that every hour we are getting this doubling of bacteria. Now, the numbers that I write to you may look very familiar from just 2 slides ago. 500 doubled, you got it, it's 1,000. 1,000 in the next hour doubling, all those bacteria splitting, you know it, is 2,000. We give it another hour, we double again. We're back to 4,000 now. These numbers are looking very familiar. And 4,000, give it another hour, is that 8,000. In the previous problem, we were talking about money starting at 250 doubling. Well, here we're just starting at 500 and doubling. Okay, this has write an expression to show how to find the number of bacteria after each hour listed in the table. Well, after each hour, I would want to use that uh-oh, where's my pen? Hello, pen. Pen for me. Why aren't you penning? I command you to pen. Do my bidding. Y equals a times b to the x power. Anytime we have this repeated multiplication, that is our signal to use, dun, 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 where is it? Up there, exponential functions. This repeated multiplication means we're in that world of exponentials. So write an expression to show how you find the number of bacteria after each hour listed. I would want my starting amount, that's my a term, times my constant multiplier, that's the times 2 in this situation, That's not how you write times 2. I'm going to have to erase. There we go. I'm getting really good at this. To the hour. Should I make it an X? Should I make it, it says T here. I guess I'll make this a T. This is going to be my T variable, and this is going to be my N number of bacteria variables. So there's an expression. You may remember from week 1 that expression was one of our Freyer model thoughts. An expression is an algebra sentence using variables and numbers and operations. Okay, now it says write an equation. So my equation is just going to be an expression equal to an expression. I'm going to go back here to this model, and I'm going to write N equals. The number of bacteria is equal to this expression. 500 times the constant multiplier raised up to however many times you want me to multiply that constant multiplier. Okay, so we were building the a times b to the x, then we were writing it in this equation form. An equation is when one expression equals another expression. Use your equation to find n when t is 0. Well, just a moment ago, we were talking about what happens when an exponent is 0. And now they're wanting us to use that exponent being 0. So I'm going to write down here, n equals 500 times my repeated multiplier to the 0. Now, we already know what's going to happen. We know what's going to happen. When t is 0, we should get 500. We should get that number. It's in our table. But they want us just to show that. Okay, so use your equation to find out what happens. All right, if I am going to now simplify this, I'm going to go back and start using Pemdas. Pemdas is my order of operations. And anytime I'm simplifying an expression, I need to use it. So what does it say? It says do exponents first. The parentheses is just a 2, so there's nothing to do. Now we go into exponents. So 2 to the 0 power. Well, we just reviewed a moment ago that any number raised to the 0 power is 1. Okay, I did my exponents. Now it's time to multiply or divide. And that is going to be 500 times 1 is 500. So my n equals 500, which we just got done saying up here, duh, it was already in the table. But that's okay. They asked us to do it, and we did it. Use your equation to find n when t is 0. What does this value of n mean in this situation? So it means you're not moving up. I want you to move up. We'll try this. There we go. In a biology laboratory, 500 bacteria are reproduced by splitting every hour on the hour. Each bacterium splits into 2 bacteria. So this was the starting amount of bacteria. This is when the experiment began. So again, moving down here, I command you to do my bidding. There we go. N equals, oh, not N equals, sorry. T equals 0 is the starting amount, or the start time of the experiment. And you know what? That's it. We finished it. Yay! Okay, if Schoology ever starts working again, I will put this up online. Take care, and I'll see you tomorrow.